So let's start by looking at the radiative dissociation. I drew the reactions on the previous slide with one arrow, but of course this reaction is always in equilibrium. So we have a back and forth reaction basically that balance each other. So we have a collision between X and Y forming an excited complex here, XY star, that is energetically still on the same level as the sum as the two reactants X and Y. And to actually form a stable molecule, it has to get rid of the surplus energy via radiation. So this is the tau R, is the radiative time scale involved, such that we can have a stable XY molecule plus an emitted photon. And this basically has to be balanced by a dissociation of this excited complex before the thing was able to actually get rid of the energy by emission of an photon, which is subject to the time scale of the spontaneous photon emission, so the A coefficient of this complex. So what we have is basically, we have the X and Y here on this figure on the bottom left. We show the energy surface of the X plus Y approaching each other. The X, the R here shows the distance between X and Y. When they approach each other, they are actually approaching something like a repulsive potential, and they form here this complex XY star. And if this complex is able to fast enough emit a photon, it will basically at this distance move to a lower energy level and remain bound. So what we have is a comparison between the time scales that are necessary to actually emit a photon, which are here the order of 10 to the minus 2 or 10 to the minus 3 seconds, compared to the actual time of the collision, because the collision moves that that the two approach each other and then like move apart again. And this takes place on a collision time scale in the order of 10 to the minus 13 seconds. Which means just comparing the two time scales, we can estimate a probability of how many of these events are necessary for one molecule formation. This is just the ratio between the two. So we have a molecule formation only in 1 out of 10 to the 10 collisions. This process becomes much more efficient if we have additional energy levels that we can use to actually park, so to speak freely, to spark our complex. So we have again here this repulsive complex energy surface, the potential between the two separate species. And when we have, for example, here an electronic energy surface of an excited state, then these are actually bound energy states that our repulsive potential crosses, so that it can actually remain longer here before it may fall down onto a bound molecular state. This is much more favorable because the radiative time scale from these electronically excited states to the ground state are much faster, only 10 to minus 8 seconds, so 6 orders of magnitude faster, compared with the collision timescale, gives this an efficiency that is increased to 1 out of maybe 100,000 collisions. So the efficiency to act for a collision to actually form a molecule can be enhanced if we have electronic states available at an energy range that might be reached during the collision event. This makes the radiative timescale shorter. And we can have the dissociation timescale longer when we have, for example, a larger molecule or so a wider potential energy well, or when we have energy barriers for entrance channels and so on. This might make T dissociation longer. The difficulty here is that these radiative association can not easily be measured in lab because they will always be just a non-dominating small number of events compared to the much more common three-body processes that will dominate under our lab conditions. So many of these rate coefficients are based just on theory, which then gives us an overall uncertainty of like 1 or 2 orders of magnitude, so a factor of 10 or 100 uncertainty in the reaction rate of these astrochemical reactions. Just to give you an idea how experiment compares here to theory, this is the reaction that we were talking about, and typically the rate coefficient is determined by the ratio between the back and forth reaction. But in our lab, we will have like a mixture of these two reactions actually taking place, so that we will find an effective rate coefficient that mixes the two possibilities, and this is actually what is measured in the experiment. This is what we actually need to know for our astrochemical computations. So we need to correct our measured efficient rate coefficient by the three-body rates that we have to try to disentangle and measure independently without any radiative association component. We have also the possibility to perform an associative detachment. An example is, for example, that we have H plus an electron forming an H minus, so for charge conservation, plus an emitted photon, or an H negative colliding with a neutral hydrogen forming molecular hydrogen plus an electron, which is a fast process. Now the difference between fast and slow associative dissociations depends on the shape of the energy surface of the particular reactions. So for example, in this particular case, we have here the energy surface crossing between the negative and the neutral variant of the molecule, and this allows for a fast transition from the one to the other, while non-crossing energy surfaces, like in the example here, require then a transfer between the two that involves then the emission or the absorption of a photon, which we saw is a slow process in the ground states, and therefore the overall reactions will be slower.